do that. I'll share my screen to tell you what we'll be doing today. I promised that we'll cover FEA analysis using what we call it the Excel methods, which is kind of what you learn from mathematics, the matrix topics. If you're doing math with Ken or you've done it in the past, I don't know about with students. The matrix method is widely used for in mechanical engineering, especially when you're trying to perform some truss analysis to find the displacement on each member, or even different parts of cantilever or those I-shaped beams. So today, what we will do, we will learn the mathematical way calculations using Excel files, and we do to compare it between the FEA analysis using SolidWorks files. And instead of using the normal solid, we use the joint method on how can we determine these files. So this is an example existing one of the textbooks. We'll go very quick through the theories of it. So we technically, to calculate the frame element stiffness matrix method, we have what we call it the coefficients K. It's the relationship between the Young modulus for that bar or that element, and multiplied by the area, which is the cross-sectional area, divided by the length of that bar. This PowerPoint will be published for you with the Excel file as well. And then you analyze the beam with respect to the angle, cosine, and sine theta. You find the equations to develop a 4x4 global K matrix to convert the local K values to the global one, and then we can solve this with respect to mathematical equations. Of course, it's required some using extra things. You haven't used in Excel files, how we activate them, and that's what we will do the step by step. So those K values, which I just put it there, will be multiplied by that coefficients with the cosine theta square. And today we'll also work with the PSI system units, ANSI standards, which is easy as well to change that in Excel files or as well in SolidWorks. So it gives you the possibility, how can you work on different unit systems and you don't be afraid if whatever is face you, because now with the software changing from one system unit to another one is very simple. Yeah. Do you have questions, Siobhan? I will share it later, as I mentioned there. Yeah. So example, the system contains 2 elements and 3 nodes. The nodes elements are labeled as shown below. So you have kind of like a fixed support here, fixed support there. This is then beam, and the other one connected to that node, and the beam connected to the other second nodes. So what we call in this system, we have obviously 3 nodes, node 1, node 2, and node 3. And each nodes, or the 2 nodes, will have an element. So we have element A between 1 and 2, and element B between nodes 2 and 3. The information given to us is alloy steel with material properties 3 times e to the power 10 to the power 7. The diameters here are everything in inch. Diameter is 0.25 inch, and the length is 10 inch. The area, it's very simply, we will show you how to set up that to find it using Excel files as soon as you set up the values. And how can we find even a non-existing dimensions? So for example, if I want to determine the length of this element B, you have the 6 inch and the 4 inch, and using the Pythagoras equation, and you can determine that distance. Okay. By the way, not necessarily in SolidWorks we need to know all the distance, because SolidWorks allows you to draw this very easily and simply with going through it. So to start this question, I will split my screen to 2 parts. One is the Excel file, and the second one is the PowerPoint, and we follow the steps. And again, these PowerPoints will be available at the end of this session. So I will copy this here. You don't need, you can start with me at the same time with the Excel files. the drawing, so we'll help you at least to set it up. All right, so I could put the information as we have them here. So for example, I would call it example 1. Information given to us, E for steel equals the value for that. It's 3.00 E plus 7. Why I'm doing it in plus 7, that's mean I'm using the scientific, not the number. The reason, because when we go and compare that to SolidWorks always produce you the plus 7, minus 7, whatever the values. And that's as easy for us to just compare the results. All right. This is information given to us like for the material properties. Now for element A, what I need from element A, diameter, it's 0.25. The units is inch. You can write that later. The length for that, it's 10. If I want to calculate the area, what is the area equals? Pi over 4 d squared. So pi, how do we write pi in Excel files? Pi and brackets. It's very interesting, not like MATLAB or other softwares. Each coding or software has its own way of how you express the pi, divided by 4. So that is just representing for me. And then multiplied the diameter square, so that to the power 2. Hopefully I didn't miss my bird mass, which is the sequencing of the operation, and I should get the same answer like you see here. And I click OK. So what I usually do here to avoid any confusion, I copy this equation on the side just for you, so later you can know where this is coming from. So here is the value, and here I'll say the equation is used or embedded in Excel files. Okay, so pi over 4 multiplied by the diameter things. By the way, some of us, we could name that instead of diameter like this one, I could just, instead of that cell here is called B4, I could just say diameter for elements or diameter. And then here you see when I come to that cell is diameter, I could write it the entire. And instead of writing B4, I could just remove that and write diameter, and the software will understand where this is coming from. I just wrote it here. It should be here actually, because that is the equation. And you can see the diameter is sensing it because I already defined it and knows this is my diameter, okay? So that as well, instead of B6, I could call it the area for that beam, okay? So that is the area. So I'll call it here instead of that area. And then when I need to calculate that, I just type area, and this Excel file understand to call that cell file called area. So here is to naming the area. Here is where you can generate the function. Okay, one of the things when we try to do, we could repeat the same thing for element B. So here, element B. Diameter is the same. The only difference for element B would be the length. The length, I don't have it, but from the figure, what I have the length of the for B, it's you have the opposite divide and the adjacent for it. So you could use the square root to find that equation. So SQRT is the square root and will be 6 inch square, don't need units, plus 4 square. And that will give me exactly precisely the element B, the length of element B. Okay. So I'll put the equation next to it so you can see what is that equation. So I always keep the equation here. So that the column will represent for me the equations which I'm interested to know. That's how you set it up. And again, where is the 6 squares coming? This is the opposite. and this is the adjacent for that. So 6 square plus 4 square, the Pythagoras rules, under square root will provide you the missing length, which is the element B length. Okay, now that is B5. I will call it LA, which is length for A. Or some people, they like to put underscore A to just distinguish it. And I click enter. So that cell, instead of has a different names, always if I need it, I'll call it. And this one would be L underscore B. So the length for element B. And click enter. So you see every time when I want to call here, as an example, L, it will identify for me in the Excel to say, hey, I have the value for LA or LB. Do you want, which one of them do you want? And this will be very helpful for having a proper engineering sheets, which you can recall any values without you search for them. This is very useful because you don't want to go back and search, where is the length for A? Where is the length for B? Where is the area? Where is the K value or the Young modulus? The same thing here. Instead of B2, I'll call it E underscore steel. So that way, if I want to calculate the Young modulus for the alloy steel, I just write E underscore and then will search for me. And again, you don't need to search always all. You just put the E and you find suggestions coming from the software. Please, for the people who are online, if you have any questions, just write in the chat so I can answer anything you want to know, okay? So that is element B, element A. Now, there is a method which we need to determine in this type of application. It's called the K, which is kind of like the resistance to calculate for that equation. So I'll type the equation here. K equals for element A. So I'll come here. Sorry. We'll add another line, insert. K for A, because they have different lengths, equals to what? Here is the value. E, as soon as I put E, will tell me, do you want that E? Yes, I want that E. Multiplied by the area. I put the area, and I think I named the area like that, small letter. And now it's highlighting the area. All of that divided by length of A. And now you see the information I just to determine that K value for them, they are already highlighted in a nice way. So E steel times the area divided by the length of that element A. I'll click enter, but at the same time, I'll put this for you here so you can see it. So you can see the equation we used for the E. Now, I don't want that to be like a number like that. I will make it scientific. So I will change that here, and you can see the scientific format, and that will come 1.47E, which is scientific number. That's if you want to change them from scientific to numbers or general or currency like we do in project management, you can always go through that. All right. This is for the first node. Can we do for the same thing for K for B? The same thing. We repeat that. So equals, the equation says E steel multiplied by the area divided by the length of elements B. And then you click enter. Again, I'll convert that to be a scientific number. And for simplicity, so if you want to follow this later, you can just see the equation next to it. And that way is very nicely, you can see equations for each one of them. Okay. Everything is okay, especially for the people online?
Hey, Mohammed, question.
Yes.
How did you convert that scientific number again for
Okay.
KI?
So I highlight the cell, and I go to full screen from home under home tab, you can see there is something here is called number format. Usually it's either general or number. I go and select scientific.
Right, got it.
Yeah, and that way you can have it to scientific. Scientific is nothing. It's just when we compare to SolidWorks, I can see it the same way how SolidWorks showing to us in the way of how you demonstrate it. And these always, I keep the equations here so you can always see what we done when we set up this in Excel file. Okay, now I add another cell here. So even if I miss a cell here, you can always highlight that from the number 8 and insert, and you can add as much cells you want, which is not a big deal. And that's something I can push the elements. I'm kind of arranging things to be nicely. All right, so if you look to this, we're right in this using insert shapes. I can put here. So that is technically theta, which I'm interested to know or to determine. I'm using equation editor. So that between the 6 and 8, that element A, it could be analyzed to cosine and sine theta. So one, it's in the horizontal direction, cosine theta, and one in the vertical direction, element A, sine theta. So theta is very important for me. I need to determine that theta, which is the angle, will help me to go through it. So in mathematics, we just write tan inverse 8/6. But I'm not using calculator. I'm not using my hands. I'm relying 100% on using Excel files. So theta for this one equals, we use the following command, equals A tan A 2, and you put the brackets 8 and 6 for the values, and you close the brackets. That will give you the value for it, 8.286. That is reading in radians. So I'll put here to make people understand what we've done between that definition, so you can see what we done is the theta in radians. And the equation we used here, very simply, I'll type it next to it so you can see that command, 8 tan to 8,6. That is equivalent to the tan inverse of 8/6, which will determine for me the angle we were interested to find. Now, again, if I want to change this from radius to degrees, it's not important there, but I'm showing you if I want to do theta in degrees, just a show. There are multiple ways to do that. One is convert units, like you use the convert and you put the radians to degrees. And the other one is just you use the formula sheet for it. So what is the formula sheet? Equal this angle multiplied by the ratio is 180 divided by pi, and then you make sure the brackets are closed the same, you get the angle 36. Now, again, with angles, I don't need to have this scientific. I can go back to show it in normal numbers or general. It's just to show you. This is just an extra. There is another command we use. It's called convert. Convert the value you want to convert, comma, the angle, and you go through it. So convert, and as soon as you write convert, you put the brackets. It tells you the information. Number you want to convert. So say I'm going to convert this one. From units, so comma, I'm converting from radius. It sometimes will show you to where you can find it, to degrees. Sometimes can pick it up, sometimes doesn't pick it up. It depends on what we selected. Oh, I didn't select them right because I didn't find them. So let's search them again. Radius. It's something called radians here. Kelvin, I can see the temperatures. So technically there are many options for it, but we don't need to do it that one. Did I see radians? I saw something. That is command allows you straightforward to convert from units to another unit. So in this way, I will just I will stick with the first one because I couldn't find the right, like how they wanted the shortcut for radians and conversion. So I'll put that equation here just for you to see what we've done to convert from radians. But technically, I'll be working in radians in this example because I'm using the SI units. But it's just in case you want to convert to something for that. Okay, go back to the table. Now, I want to create my elements here. So I could create a matrix of 4 times 4, which is equivalent to what we've seen here earlier, this one. But following this example here. So what is the example? It should be here, x1, y1, x2, and y2. Kind of we're doing the analysis for each node. So x1 and y1 is for the first node, node 1, node 2, and x2 and y2 are there for the node 2, because that element A, it's between two nodes, node 1 and node 2. So each node has two components, one in the x direction, one is in the y direction. So to avoid people missing where we're going, I always recommend to put your coordinate so people can understand what's your positive, what's your negative, where is your x and where is your y. And I put here x and Control C, Control V, and here I put the y. And that way people understand where is your x, where is your y, that it's representing for node 1. The same thing is applied for node 2, which is at that point, okay? So when I need to do that, technically, I need to, as well, to determine for my angle, the cosine and sine theta. So first, I need to do here cosine. I'll write cosine here so you understand. Equals cosine, the value for radians, the theta, V8. Now, I'm not happy with V8. Because I want to change that to call this cell theta in radians. Why? Again, to make my life easy. So now when I can equals cosine, here I just say theta radians. And again, because that is part of me to make sure I can call theta radians anytime. But I will have a problem because the other beam also has a different angle. So I need to be careful to name that cell something that doesn't interfere with me. So radians, and I call this one A. And now see, when I updated that, it didn't change anything here because it didn't pick up that. It says, where is it? I didn't click enter. So you bring here and updating it for elements A. And now theta, radians, A, enter. It doesn't let me do it, or because I'm using it, it doesn't let me. Come on, I want to change it. Theta underscore. For some reason, when I click enter, it doesn't let me change it. Okay, we can change the other one, theta radian B, and then we go through it. Should have done it earlier. So cosine theta. Oh, there, it was reading there. Just didn't like it. All right, so it did make the change. And here would be the other one, sine. So I put here equals sine theta radians for A. and that will be 0.8 and 0.6. So I just did sine theta. And to make that clear here, you just put theta, radians, A, just people, like when you try to find what we've done here, and here I'll put sine theta underscore radians A. One is cosine, and that was sine. So these are the values for them.
Oh, I see.
Yeah.
Right. Sorry. So it's in the equation.
Yeah, I should add a new line here. Insert. Well, will ruin my line here. Let's do it that way. Control X, bring that one here. Control X, bring that one here. And the equation, I can just, let's tidy it up. So people, you get it exactly what we've done. Let's continue with the tidying up, okay? Cool. Okay. I like to just make this more obvious. Okay, so x, y1, x2, y2. We need to follow these equations. It's a big process, but if you look into this equation, many of them, they actually are repeated. And you say, what do you mean by repeated? So I would show you, I'll just minimize that size. And then we increase the scale size for this one. We make it 20, maybe that a good size. Yeah, so you can see it. So if it's k cosine square theta, and we are taking the answer for that, we're not doing cosine, and that's why I did the cosine and sine theta easy for me. So I came for the first value, equals the k for a. So I could type, have I defined that? I go and check for that. Yes, it's not defined yet, so I'll call it KA. Just to define that, KA. So here would be equals KA multiplied by open brackets, and then I need to find cosine theta squared. So that is cosine square, and then you get the first answer. I would do them numbers now, and later I'll convert them to scientific, okay? If you look to that one, k cosine theta square, it will be repeated some places. So I would do the first x1 till all of them. So let's continue with the second one. Equals k, okay, multiply by cosine theta multiplied by sine theta. The third one. So technically what I'm following this table here. Minus k a brackets cosine theta squared. And then the last one for this x1 is minus k times what you have is the cosine theta multiplied by the sine theta. Now, life is easy, and we are lazy people. So this one, you can see k cosine theta sine theta comes here. Just copy paste. I can just say this equals that. Life is easy. And that is k sine theta squared. So equals ka multiplied by open brackets. Here will be sine theta squared minus cosine theta sine theta. So already got the k cosine sine theta. So equals this one times minus 1. And we give you the value. And this one is equals this times minus 1. Because it's the same. If you look to k sine theta squared, here is negative sine theta squared. x2, it's minus cosine theta. So I already find cosine theta. So it's this one squared times minus 1. And then you come to this one minus cosine theta sine theta. So is this one times minus 1. And then this is k cosine theta equals this one. And this one is equals k cosine sine theta equals to this cell. And then go to y2 equals k cosine theta sine theta times minus 1 equals minus k sine theta. So that one times minus 1. So I'm just following the equations, equals k cosine sine theta, which is this one, equals k sine theta squared, which is this one, but in the positive, so equals that one. After I follow these equations, now I can change them to scientific. Table them nicely. Just put all borders. And I'll put them there. And now I'll show you the table is generated here. It's exactly, they match the numbers. And again, because it's a metric, so it's following the same, we're not changing. It's technically we have either the 9.42 or the 7.07. There are two values for the components, x and y, x and y, x and y. And then we are distributing them based to that 4 times 4 global matrix, and we can determine the values for them. So that is technically the first one for what we call it element A. I would just type here, element A. I'll give you a break a bit to catch up. Make sure you're there. All of you got that table or still working on it?
Just double checking.
Yeah, just double checking the numbers. So in the X, Y components for node 1, we have 9.42 and 7.07. For the second one, we have 5.3 and yeah, those are the two values, 5.3 and 7.07. Done? Done? Okay. That is for elements A. For elements B, we need to repeat the same process, but slightly different. So let's go to the PowerPoint slides. So for elements B, we already calculated the E steel and the K value after finding the length. So we find the K value for element B, it's about 2.04 e to the power 5, which is 10 to the power 5. Now, what is missing, we haven't done yet, is the theta we need to determine. And here is the trick with that theta. So first I will write the equation, theta in radians for element B. What is the theta and how can we determine that value? So theta is working between the angle 4 and 6, but would be in the negative. Why? Because if you look carefully, this is the node 2. The angle we're trying to determine, it's this one. Or how you find it. So you have kind of like 4, and a replacement for that will be the 6. But because we're going, I assume my positive x is upwards, and this is downwards, so therefore I need to use the negative value. So that's why I put here x and y where is the position. So y is upwards in the positive. If it's down, the angle, so I need to take into account. So theta will be here using the same command, a tran, like similar to what we've done here, a tan 2, so equals a tan 2 brackets. You would choose 4 and minus 6. And as soon as you click that, will give you a negative gradients angle. I will call that one theta gradients for B. So that to distinguish it between A and B, okay? Now, we need to do the same thing to find the cosine theta gradients B and sine theta gradients B. So for the elements B, we need to find that. So here is very simple. Cosine brackets theta gradients B. So because I wrote it, I don't need to go and select it, equals sine theta gradients B. And then you can see it's by default will select that for me. So now I got the cosine and the sine. I'll write the equation next to it so you can see what I've done. So in that way, you don't say where this is coming from. I put them all next to each other of them. So if in case you want to follow that later, I'm putting all the equations so you can see the equations we set up in the system. Okay. Now also, I could make my life easy. Instead of B17 and B, because you see I need to use always cosine and sine. So I could say that one is cosine for B, and this one is sine for B. This technically, when you do the multiplication, because we have many numbers, I can just search for them and very quickly determine these values. So this sine B, cosine B. And that way make life easy for everyone to go through it. Again, if I want to avoid any of these numbers, I could just put them scientifically, but we can arrange that very soon. Okay. Now, I will do this table 4 times 4 here. And I will call this one x1, y1, x2, y2. For which one? We're doing it for element B. So the first one we did was for that element between node 1 and node 2. Now we're moving between node 2 and node 3 for element B. So we're going through that line. Okay. And I'll tell you why I did them that way, because I will use some of the in middle between them. I know how I deal with them. Okay. So we have the following equation. I would just put it there. Summarize this one so we can follow this. Enlarge the text size. We make it 20 so you can see them clearly. Go back to this. So exactly that equation which we designed before or we follow before, I need to follow it up and do the same thing what we done before. So the first one, and I don't need to look, is just K underscore. Did I do the KB? didn't pick up. So I'll go and check. No, I didn't do KB. So, okay, escape. I come here and I call this one K underscore B, and that way would be easy for me. Okay, now equals KB, it's already picked up, multiplied by cosine theta. So I put cosine B to the power square, and I get the first value. So I'm following exactly this one. And I will repeat the same thing for the rest of them. Equals K for B, not A, please choose B. Oh, I didn't finish. By the way, if I lost it, I just type on the top. So here is my equation editor. Multiply by cosine B, multiply by sine B. And that way you can see the cells which are important for me, they are highlighted there. I can zoom in, but let's do it that way. When you zoom in, you just need to enlarge the text here. They will not show up. Or zoom out. Okay, now I'm this cell minus K. So that is just minus K cosine. So I can be just lazy. That one minus times minus one. And this one would be that one times minus one. So it give me the positive number. Because these technically K cosine theta square, and here is minus K cosine theta square, and here is K cosine theta sine theta, and minus. So technically they're the same values, just you inverse the values for the sign for them from positive to negative. Now, when they are negative, negative times negative will be positive. Okay, I go to Y1. What do I have? Y1 is K cosine theta sine theta. So technically we've done this one already equals to this cell. And here is K sine theta square. So equals K underscore B times open brackets sine underscore B. Make sure that is goes square, and then you close that. You get now for the K sine theta square. And now equals K cosine sine theta, which is similar to this one, times minus 1. And then this is minus K sine theta square, so it would be this we calculated times minus 1. So these are the same. It's just the sign. Now x2 equals minus, so that one times minus 1 equals this minus, so equals this value times minus 1 will be positive. And this one is K cosine theta square, so equals to that. And this one is K cosine theta equals to this one. So I'm just following exactly the equations. Equals minus K cosine theta, so that one times minus 1. Minus K sine theta, so equals, that is the K sine theta, but minus 1, multiplied by minus 1. Equals K cosine theta, so it would be this one. And the last one, it equals the K sine theta square, which is this one. Again, I want to convert this to scientific, highlight them, and you can make them all scientific numbers. And also, something I like always is to just show them nicely. So again, this equation, if you look between this one and the previous one, they are the same equations. It's the same thing. We just follow the signs for them and how we go through them, and you get these answers. So we found the matrix for element A between node 1 and node 2, and we find the matrix for element B between node 2 and node 3. And now we need to find how can we deal with matrix. Everything is finished now, we're going to math. Technically, engineering till here stops. It's like when it's saying no more engineering here. We switch to mathematics. And that's why math is one of the most important subjects in engineering. It's like very quickly, by the way, there was typo here. That should be T, A tan 2. All right. Are you there with me, or if you want anything to clarify, please ask for it before we go to the next step.
Can you please give us 3 minutes?
Yes,
Mohammed? Just
3
finishing it off.
Take
That's it.
5. Take 5. I'll pause recording. Pause. No. Resume sharing. Pause recording. Resume recording. Oh, God. I'll repeat that. So take a break and then we can repeat that, because that is the most important process for it. Otherwise, we'll go through it. Okay, you can do that again. Okay, so let's repeat this process because I forgot to click record. Delete. Yeah, we need that. So again, I define the Fx, Fy, which they are the support reaction forces in the X1 direction suggested from the fixed support. At Fx2 and Y2, we have the 50 in the X direction, but nothing in the Y direction based on my coordinates. And then Fx and Fy for the third node, it's unknown. The displacement X1 and Y1, because they are fixed support, is 0 and 0. X3 and Y3 at node 3 are 0 and 0. However, at X2 and Y2 are known. So I need to determine that. So we create here an inverse for 2 and 2, X2 and Y2 array. And that we just highlight these 4 cells, go to function. From function, we change it to math and tricks. From math and tricks, we go and select M inverse, matrix inverse. And then click OK. We're trying to determine what's the arrays in the middle, the one we are related to node 2. It's the common between element A and element B. We click OK. Now we get these values. Here we write X2 and Y2 to find those displacements. So we do again, select these, go to function, math and tricks, but we find the function is called M mult, which is related to have 2 arrays. One is related to find the values we just found from the array here. These ones, the inverse for X1 and X2. And the second one, we go click tab, we find the 4 related to the force applied, and then we are happy with that. We determine the values for this. Technically, we can just type here, this is for the X, and this one is for the Y. And I make them all scientifically. So now we're good. Any questions so far? Again, we are using Excel files with a bit of math techniques to find matrices in a way you solve the question. Is it done? Not done yet. Nothing is done. Now, pre-select the 6 cells because what was missing, we need to find Fx1, Fy1, Fx3, and Fy3. I didn't label that correctly, so I'll say 3 and 3. Okay, so we need to determine these values. So how can we do that? We need to create a new function here. I will highlight this with a different color. Let's use purple, light purple, don't want something, and make it squares. So we highlight this table, go to function. Again, we go to M. Now, what we have here, we need to select 2 arrays. The first array, it's selecting everything inside this matrix, the 6 times 6. And then, so that is the first thing we select. And then tab, we select the answers we found from displacement. So first we select the inside matrix 6 times 6, and then we select the displacement. We just found the 0, 0 and the two values. And then we click OK. You find by default, this table will generate it for you what the forces in FX1, FY1, FX2, 50, FY2. FY2, by the way, is 0. Do you see how mathematically it's giving you a very small number? Because if we change that to a number, it's 0.
Yeah.
This is it, but you say, hey, why? It should be 0. Why are we getting weird number here? But that is just, in math, 0 is not 0. It has a something. That's what it is in math. Okay? So I always go and change it to number again to prove this is really 0. It's not we faking it or we give you a wrong answer. And sometimes I don't like significant figures here, so I just make it like that way. Okay? So that technically what we find, the support reaction forces, when you replace these support reactions at node 1 and node 3, FXY and FX force and FY force values. So they are imbalance. We're working here. Any questions so far? Again, yes, let's do that again. So I delete that table. Now I need to determine the support reaction forces. I know only there are forces that this one is 50 pounds and in the X direction, nothing in the Y direction. So I highlight this table, must matching this FX1 to FY3. Go to functions, make sure it's a math and tricks, search for that M mult, because to erase, we tell you what you want to do. So first I'll select the inside array, which are giving me all the values for K's inside. And secondly, I need the values for the displacements, and then click OK, and you go and you find it that way. Now, the 0 is already set up, so the Excel already embedded. By the way, one thing about good Excel, if you change the question, technically, you don't need to do much. It will calculate everything automatically for you. So you say, what do you mean? If I change one dimension instead of 4 or 6, I just go and initially change one value, and then we'll recalculate everything for me, like from scratch. So here is showing you the support reactions at Fx in the X direction is -33, is going downwards, not upwards. And in the Y is going the other way direction, which is -25. And then for that node 3, you have one negative is going downwards in the X direction, going that way, which is -16.6 pounds. And the 25 is upwards to equilibrium that truss analysis. Okay. Now we want to determine the stress in elements. Oh, before the stress in elements. Let's do this in FEA. Okay, we got the values, right? Let's check that. Does work in FEA. Okay, so how it works in FEA? We go to SolidWorks. I have billions of SolidWorks. I want 25. Let's do that in SolidWorks, because now we want to justify our results. And you remember, we learned how to calculate support reaction forces, displacement, and how can we find these values. Why is it taking a long time? Is your SolidWorks taking a long time or just mine taking a long time?
Probably the recording slows it down too.
Ah, yeah, I remember. Yeah, Zoom actually. Yeah, these computers are, I think, 16 or 8 gigabytes. I forgot. That's why. Okay, we start with parts. So we switch to SolidWorks. We withdraw the problem, and the problem is already with the following specifications given to us. I have it already in the PowerPoint slide, so I will give you that. We'll split my monitor to 2 halves again. By the way, if you work in FEA analysis, 2 screens is not even enough. I'll tell you that. We always, when we do FEA and CFD, I never work with 1 screen, minimum 3, because you have multiple things on working in the parallel and go through it. Okay, so first of all, file, save. I will call that in a folder on my desktop for me because I'm using Wintec computer. And desktop, I will call it truss analysis. Part 1, it's okay, keep it the same name. Things we need to do here. Because the problem, it's all in PSI units. So I will show you some, I'm just adjusting my screen, as you can see everything. Okay, don't need that, minimize. First of all, change the units to IPS, inch, pound, seconds. And that's a nice thing, some flexibility with the software. Also, come to this gearbox and click on it and go to document properties, change over drafting standard from ISO to ANSI, different standards. So again, where did I go? I came here and I changed the units to IPS, inch, pounds. And with that gearbox you see on the top, I'm zooming down. When you click on it, you can go document properties. I change from the setup by ISO to ANSI. So these are different standards used by industry. Okay, and you click OK. Front plan, it's our plan. You go to sketch, you choose line, you sketch from the origin, the following lines. Now we dimension. That box is very small to see it. I would enlarge it so you can see the dimension. Smart dimension from that point to that point, it should be 6 inch. And from that point to that point, straight line, that should be 8 inch. And then from that point, that should be 12 inch. Now, this point with this point, they should be horizontal, on the same horizontal. So when you see that green horizontal line, it means they are going through the same line. Okay. Exit sketch. So very simple. Truss analysis is very simple when you draw them. Do you want me to repeat that? I'll repeat this. It's recorded. You can do it anytime. So front plan, make it to face me. Go to sketch, select line. Start sketching from the origin. This one, whatever is the origin, go up, go down. You can match it here. Use smart dimensions from this point to this point. It's 6 inch. From this point to this point, it's 8 inch. And then from this point to this point, it's 12 inch. Ensure this point with this point, by the way, later we call them nodes, are horizontal. So technically they're on the same plane. Yeah, that is 6, 8, 4 and 8 is 12. Yeah, we got that. We're correct. No problems. Okay. Happy with that? You just click exit sketch. Features. Extrude. Extrude, you first extrude that line. No. One mistake. Sorry. Features. You go to reference geometry and we create a plan because I need to create a cylinder truss. So it's a circular pipe or truss. So in that one, you select that line first. I'll repeat this step because maybe I jumped very quickly. Features, you go to reference geometry. Under reference geometry, what you want to reference is that line. That's the first thing we select. Make it perpendicular. You click on perpendicular. You can see it selected that perpendicular. You select that point. That will tell you where is your plan is now allocated. You click OK. It's created the plan 1, technically perpendicular. Why I need that? To sketch a circle at the center for that plan. I'll repeat this again. Delete. You go to features, reference geometry. If you can't find it, just search here. Plan. Select the line. Perpendicular. Select that point. When you come here, and then you can see the plan will be in that direction. Okay. Now from that plan, I need to sketch a circle. That circle, if you remember, the radius was 0.25. Make sure to rotate that before you accept. Yeah, that circle is the center of the line and it's plot on plan 2. Exit. So that is just a circle plot on plan 2 because I deleted my plan 1. Same thing I do. Repeat this. Features, reference, plan. I would do it on this other bar or other element B. Make that perpendicular. Choose that point. Change, flip normal. Make it to go upside like that instead of going that way. And then you create, for me would be plan 3, for you is plan 2 if you haven't deleted anything. Now we still have plan 3 active. Sketch, circle from the centroid of that point. Smart dimension 25.25 inch. If I'm doubting something, always go and check. Is that really sketch on plan 3? Yes. Is that correct? Yes. And then you exit that. So I sketched 2 circles from the beginning of plan 2 for me, possibly plan 1 for you, and plan 3, possibly plan 2 for you. Now I need to extrude that. Features, extrude. Will ask me, what do you want to extrude? I extrude that circle to go to where? Up to vertex. Vertex is like the point. This is my vertex. That's all. You're happy with that? You click OK. And then you repeat the same thing. Extrude feature. What do you want to extrude? You want to extrude the second circle. And then you say up to vertex. But here you need to be careful. You select that vertex, but untick merge results. Because if you tick them, technically SolidWorks treat them as one piece. And that will not give it that nicely movement because you have a force on top and not welded. So you untick, don't click, keep clicking that merge results. So that will generate for you the second. So that is technically your front view for similar to the truss we were seeing before. Okay. Now I don't need plan 3 and plan 2. They are extra, not needed. Hide. Based on the question, if we go back to the main question, what do you see here? Sorry, I'm having Difflan, my throat stopped playing me. We have the following. Fixed support at this node 1, fixed support at node 2, node 3, and there is a force applied at node 2, which is the 50 pounds going in that direction. We need to be very careful with this one. How can we treat this everything precisely? So SolidWorks is finished here. Now we go to the FEA analysis. We just done the SolidWorks. Okay, file, save, just to make sure I'm saving what I've done. I will go and activate SolidWorks from add-ins. It's active for me, but just for you. You make sure these boxes are ticked. And I know they were ticked because I can see them there. You start a new study. Please, we're not doing 2D. However, we'll be doing 2D. So don't click on use 2D simplified. We're still doing a static analysis. Click OK. Now I tell you, how can we treat that? You select both beams and the parts, right click on them, treat selected bodies as beams. That way, we'll give you an error to say, hey, what's going on? You tricked me. Do you see that in the static on the top? It's became like an error, red one. So we treated them now like a beams. Beam could be different shapes, I shape, T shape, circular shape, the beams. Now, SolidWorks understand we're doing a truss analysis problem. Okay. Now, after we did that, we could right-click on join groups, edit. We tell it, can you calculate how many joints we have? Yes, we have 1, 2, 3, similar to what we had in the question. You remember the knots, the joints. So 2 elements, element A and element B, connected between those 3 joints. Right-click on both beams and select Edit, Apply Material, and we select Alloy Steel by default. It's already there. You just say Apply, because when we do FEA analysis, the software needs to understand this is a material properties, because we'll give you what? The Young modulus, the elastic modulus we needed to do the calculate, to compare to the calculations. You remember when we had E used in our question? Apply and close. Now you can see the material properties already applied. Right-click on these 2. Edit definitions and change it to truss, because we're doing truss analysis, not beam problem. That will understand. You remember from mechanics engineering when you did the truss analysis of the question? So re-edit this to treat them as a truss. And then you click OK. Do we need to do the beam direction when we did the truss analysis? 1 second. I don't think so. By the way, it's almost done. It's just we're fixing the things, but I just want to check if we need to give that the truss analysis some definitions for it. Truss. Yeah. Apply. Yeah, that's good. No need. Fixture. Fixture advisor, we select fixed geometry. So what we're fixing this. So technically that one, joint 2-1 and joint 4-1. These are the joints we are fixing. Technically, these 2 as shown in the figure, you can see it in the PowerPoint slide. After the fixed, what we do is we use another fixture, but use reference point. So right-click on fixture, fixed geometry. Here we use reference geometry. The joint will be that one, the joint 5-1, the middle one, not 2 in our example. And from that tree, we select the plan which we need to be a reference for. That would be front plane. That's where we did our movement, okay? And we give that normal to plan with a 0 displacement. So we just activate that and we keep it 0, that one. And happy with that, we click OK. Now we need to apply external force, the 50 pounds, as you can see there. So right click, force. The force will be applied on the joint. Make sure to select joint, activate joint, and then select that joint 5-1. From the joint, you need to select the face edge, which direction to reference to front plane again. I thought I selected, yeah, front plane when you see it. Change the unit from SI to IPS. We select the option along plane direction 1. Give that value of 50 pounds. Now you can see the arrow precisely where it's going. Do you see it? The purple. It's going that way, which is exactly matching the question with 50 pounds. If we wanted to go back, we just click on reverse direction. By this stage, that is the value. We go through it. Happy with that, we click OK. Now, because this is a simple question, the mesh is very simple. Right click on mesh, create mesh. Automatically, the mesh is done for us because it's technically, it's very simple question. Now, everything is ready. Run the study. It's give you the values very quickly. But what we got an answer in our Excel file is not matching what we can see here. We need to change that one. Double click on stress 1. Change the unit to PSI. Instead of upper bound Excel, use the Excel and keep it automatic. And you get that it's to be equal to 8.488. That is the axial force which we found for this question. We haven't calculated the stress. We calculated only support reaction forces. Displacement. Right click on it. Edit definition because it's showing me the values in millimeters. I want to see it in inch automatically. You see the value is 3.217. That is the displacement, almost what we found. 3.24, 3.217. And it's giving you. If I want to check the axial direction, I could just play, animate, slow the animation, it's too fast. That's technically how the beam is corresponding towards that load. Okay. So we could control print screen or snipping tool. Use dip. Control. Bring that one here. And bring it on the side here. So that's technically what we determined from the things. Do you remember how could we find the support reaction values? you see the values? And the one we found from the calculations, that's exactly how they look like. The minus 33.33, minus 25, and then you have the 0 and 41. That's just to give you. And if I want to find the points here, because it's giving you the one we found is the 2D, they give us here the sum of Z as well, and the resultant as well. Now, if I want to check as well for this one, update, you see the values will be whatever we got from the other point. And this one, you get X sum, X and Y. It's best to do it one by one so you don't confuse the software. Calculate, that will give me the minus 16.66 and the 25. The Z is nothing in the Z direction, is 0, because remember, we solved the problem only 2D, X and Y. We didn't do Z. Z does mean we're adding if there is a motion coming towards me or going opposite to my direction. So that is to justify what we've done is correct, because see, the calculations we performed in Excel file and the FEA analysis is giving me identical results. Okay. You go back to the Excel file again. How can we determine the stress in elements to compare what we found from the figure? So I'll go through the notes first. So the stress, to determine the normal stress in each truss member, one option is to use the displacement transformation equation to transform the result from the global coordinate system back to the local coordinate system. So X is equals the length times the X for it. So that will give us the displacement transformation equation. So you have X1, Y1, X2, Y2. That's for node 1 and node 2. And you have the equations. Here will be only cosine and sine theta. There is no K to take into account. And they show you the local force displacement will be positive 0, negative 0, 0, 0, 0, and then negative 0, positive 0, and 0, 0. And then you do what we've done in the past mathematically. How can we determine the values? So let's do it step by step. So elements A, we write element. Why we write it when it's already there? Element A. What do we have from element A? The equation we're trying to determine from element A, it's X equals LX. We have the following value, X1, Y, X1, Y1, X2, Y2. So following this equation, I'm showing to you on top here, is just cosine theta minus sine theta, 0, 0, 0, 0, and you go through them. So I can simply put the zeros first, and then I'll show you how can we distribute the values. Let's go in here, 0, and then that is here is 0, 0, 0, 0, 0, 0. Okay, so here, it will be the first one. If I've done it correctly, I don't need to go and search for it. So I could search cosine A. See, I haven't done it. See, that's the problem. And that's why I tell you, the good engineers will really do this very quickly. So here, you need that one, cosine A, and that one is sine A. And that is all to save your time. So you don't go back and you just call the cell. So here would be cosine A. You can see it there. Enter. And that one is equals minus sine A. Enter. And this one would be sine equals sine A. Enter. And this one equals cosine A. And then here would be cosine A. And this one is sine A. I forgot the equal. Sine A. And this one is minus sine A. And this one equals cosine A. Very simple. Like, because we have them, the cells, I follow the equations. I put this in a square. I make them middle cells. So to be life easy for us, X, Y, we go through them. Okay. Mathematically, how can we deal with that from what we've done in the past? Remember what we did? So we want to find these values, right? We highlight this. I always color them with some light color, make squares, and go to function. From function, we still with math and tricks, right? And we have the M mults. And we'll access which arrays you want to choose. So the first one I choose for it is this. Array 2, what we choose for array 2. We go to our answers here, and we select the X and Y, only these sides, because we're not doing anything related to element B. We select the nodes for elements between the element A between 1 and 2, and taking into account the effects of element A. So I select these values, and then I will get the value for it. But for some reason, it's giving me unknown in the table.
0 and you see.
Ah, sorry. Now it's good. Done. Thank you. You saved the day. So that is giving us the displacement. I like always to go to scientific, because remember the things we got from scientific, it's the one we will see in Excel files. 2.83. So this giving me the displacement or the elements for the elements A. Remember, at X1 and Y1, it's 0, 0, because it's fixed support. But at node 2, that's where we anticipate a bit of displacement, where is the force is acting on it. Now, let's find the second things which we need to determine. Force equals K times X, the coefficient times the displacement. And here would be fx1, fx2, sorry, fy1, fx2, fy2. So the analysis of the force in X and Y direction for each one of them. Here, what should be the relationship? K, do we have the K value? We already found the K value in advance. K for element A multiplied with following the local K matrix. So the K here is just to add the K. Following the matrix which is given to us will be 0 equals KA, which we already did calculate. and then 0. I'll change them all to scientific. 0, 0, 0, 0. And then for that one would be equals minus Ka. Enter. And then this one is 0, and this one is just Ka. And this one is 0, 0, 0, 0, 0. Okay, I'll change that to scientific to make sure. Oh, they're all scientific. Not really. Okay, that's better. Now we create the fx value here, another table, give it another nice light color. I'll make the table for that. Function, we use the same function, math and tricks. Where's the M? So the first one, what will be? The first values will be for us is the one we just determined here. And the second one will be the one we just calculated from the X displacement. And then you click OK. Would give us the following values: 41, minus 41.66, and 0 and 41. Now, the value we're trying to be interested is, it's the one where is the node 2, the function of X go through it. So to do that, stress equals to what? Stress is equals, here I just made the equation very small, but we can enlarge it. Stress is equals F divided by area. So that is the force we divided. Do we have the area? Yes. So if I do that, stress equals force divided by area, hopefully it's saved, we'll get 848. That is the stress value we determine. I'll highlight it in red. And the equation, I would just write it here. So stress is equals F divided by area. F is that value divided by the area. Area already just called it back. And then you can go there. If you want to do this, like to make it something more scientific, it's 8.49. Now, if we go to our lovely one, the stress is 8.488. That's technically, I can print screen this using this snipping tool, and I put it next to it, and I say what we determined from too much. So I can bring it here, and I say what we determined from that question at that joint is the red area what it's showing me. It's 8.488. The answer I got 8.49 because of the rounding numbers, plus 10 to the power 2, which is the Pascal, the axial force applied on it. And that is just for the elements it's showing to me, and you go through it. Now, if I want to repeat the same thing for element B, I follow the same table, recopy and do the same thing. And that is justifying what we've done in these calculations. How can we determine the support reaction forces? How can we determine the displacement? How can we determine the values we are interested to find for each one of these questions? Yeah, any questions, especially for the people online? I know it's a long day today, but it's a lot of things to learn. Glenn, Jacob, and who's online? And Brody. Any questions? Are you still there, or I lost you guys?
We're here.
Oh, good. That's good. So you got it there. So that is just kind of justify what we've done using an Excel file, what we've done in using the SolidWorks. By the way, this topic, some people, they teach it in strength of materials, but I don't think in widely, because if you haven't done the math 2 or the math 1 for the degree with matrices, then you don't do it. I don't think they teach it for the diploma students. I don't know about you guys from WIT. Have you done this example in other papers? Someone in the chat typing. Oh, good. Well, you're good. I don't think you've done it that one, because it's required a bit of understanding of how you manipulate matrices and how can you organize them, and you go through it. By the way, this question can be easily done in MATLAB with less time. One script does everything for you. But Excel files is widely used by engineers, and it's a tool, powerful tool. It's free access. You don't need to pay for license. Student license, always free to get it, and you can go through it. Now, if you're interested, I think that is where we finish with this example. That is just to show you how you do it in SolidWorks file. Yeah, that is all for today. I'll share this file for you now before I go. Something I haven't said to the WIT student. Guys, today is my last lecture with you. Because I haven't seen you, so I'm leaving Wintec, and today it's my last one. So hopefully you can get a new tutors and transitioning easily for you guys. So don't worry, the new person, whoever is that new person, will be in contact with you, and we go through it. A10, that is corrected. I remember there was an issue, I forgot. Yeah, that instead of R is 10, A10.
Is it still looking like full? I know.
No, rejected.
Okay.
Yeah, too much.
So Mohammed, today your last day.
I've just read through, stop recording. We are recording. 1 second.